Okay, so let's talk a little bit more about rotation. Let's say we have a disk rotating this way, which means it has negative rotation. And also, if I haven't already yet, remind me to talk about rotational vectors in class. It's a little bit confusing, but it's something we need to mention. So let's say that we have this disk that's rotating this way, okay? That means that each of the particles is moving at the same time. Okay, so there's a particle there moving, a particle here moving, there's one here moving. Everywhere on here, there's particles that are moving. And what this means, if particles are moving, that means they have energy. Okay? It means they have kinetic energy. Well, if we wanted to find the total kinetic energy of this disk, we would basically find the sum of all the kinetic energies of the particles. Okay? Now, this isn't very useful for us just because they all have different velocities. Okay, they're all going different speeds based on their radii. What they all have that is the same angular velocity because they're spinning at the same rate. Well, we know that V is equal to omega r, so we can take this and substitute it for V. So we get 1/2 m1, we'll make this omega 1 r1, okay? And this is squared. So we get 1/2 m1, and we'll move the r to the front, r1 squared, omega 1 squared, okay? And so we want to find the sum of these for each particle. Now you might be thinking, well, that just looks even messier than what you started with. And it does, but we can simplify this a little bit further. Okay, we know that for each particle, they all have the same speed of rotation. So this angular frequency or angular velocity is the same, so this will be the same for everything. So this becomes 1/2, and then we'll just put this in parentheses real quick, m1 r1 squared times omega squared. We're finding the sum of all these. Well, the only thing that we have to actually sum up here is the mr squareds. Okay, so 1/2 times the sum of all the mr squareds times omega squared. Okay, it gives us our kinetic energy. Now, let's go over here and say the sum of all the mr squareds. Okay, we're going to define this as something called rotational inertia. We're going to use the symbol I for it. Okay, this is rotational inertia. It's also called moment of inertia. And I prefer to call it moment of inertia, but you can see it both ways. Okay, now this is essentially the rotational analog to mass. Okay, so this is like rotational mass. And what it means is that something is more difficult. So like mass is a measurement of how difficult something is to move. Okay, well this is a measurement of how difficult it is to cause something to rotate or to change its rotation. Now, the bigger m is, the more difficult it is to rotate, and the bigger the radius is, the more difficult it is to rotate. Okay, you can imagine taking a yo-yo and swinging it around, and then taking that same yo-yo and attaching it to a 5-meter string and trying to swing it again. The 5-meter yo-yo is going to be hard to swing around. And so we'll rewrite that kinetic energy of rotation is equal to 1/2 times I omega squared. Okay, so this is our kinetic energy of rotation, and we can use it to find literally the amount of energy that something has that's rotating. Okay, and now we have this omega here, which makes it pretty simple because we don't have to add up all the pieces. We just have to know two things. We have to know how fast this is rotating, what its angular velocity is, and we need to know its moment of inertia, or the sum of all of the pieces of mass times their radii squared. Now this can be pretty tricky, but kind of the clue here is this summation. Okay, what that means is that we can actually use integrals. So that I is going to be equal to the integral of r squared dm for any rotating object, okay, or any object that you want to rotate. Now, we're not going to get too far into integrals. Fortunately, a lot of the work's been done for us. Right now, we're going to focus on the sum of the mr squareds, though, for finding rotational inertia. So we're going to try this now. We're going to calculate some rotational inertias, or moment of inertia. So I is equal to the sum of mr squared for all the particles. So here we have a system of particles that we're going to rotate. Okay, the first thing we're going to do is we're going to rotate it about an axis that goes vertically through the center of particle 1. So if we create an axis right here through particle 1, we want to find the moment of inertia through that axis if we're going to rotate this system. Okay? Well, that means for each particle, we're going to multiply their mass times their radius squared, okay? And add them together. Now, for particle 1, the radius is 0. And so particle 1 has no moment of inertia. Okay, so let's add these all up. So for 1, we have 0. For 2, it has a mass of 3 kilograms. And it has a radius. Its distance, so this would be 2, this would be 1. So it has a distance of 3 meters. We're going to square it. Okay. Then over here, particle 3 has a mass of 10 kilograms. And it's going to have a distance here of 1 plus 4 or 5. Okay. Now, before we do this calculation, you can see that particle 3 is going to have a much larger moment of inertia than particle 2 because it has both a larger mass and a larger radius. Okay. So we add these together. 3 times 3 is 9, times 3 is going to give us 27 kilogram meters squared. 5 times 5 is 25, times 10 is going to give us 250 kilogram meters squared. Okay, and we'll add these together and get the total moment of inertia for those 3 particles around that axis is going to be 277 kilogram meters squared. Okay, now this value means nothing to us right now. Okay, it's just a number with some units. But we're going to kind of continue working with this because, like we were saying earlier, this is kind of like the rotational analog for mass, which means that we're going to put it together with the rotational analog for force to talk about how difficult it is to cause something to rotate or to accelerate it. Okay? And what you'll find is if you're going to rotate these particles around a different axis, we actually get a different value for moment of inertia. So now we're going to rotate about a horizontal axis through particle 2. Okay? Okay, so for particle 2 now, we're going to find the moment of inertia of the system at particle 2. And I'm going to have you go ahead and do it without my help here. Okay, so you'll go ahead and add up all the mr squareds for each of the particles. Okay, so you've gone ahead and done that now. We added up mr squared for each particle. So starting with particle 1, it's got a distance here of about 2 meters. It has a mass of 7 kilograms, so 7 kilograms times 2 meters squared. For particle 2, it's on that axis, which means its radius is 0, so that would be a moment of inertia at 0. And then finally, particle 3 has a mass of 10 kilograms and a radius of 4 meters. We're going to square it. Okay, and so we get here 7 times 4 is 28 kilogram meters squared. And 4 squared 16 times 10 is going to be 160 kilogram meters squared. Okay, so the moment of inertia about this point, or about this axis rather, is going to be 188 kilogram meters squared. Okay, and so I believe before, let's see, we got that the moment of inertia from the previous one was like 200, I don't remember exactly, I think it was 276. Okay, So you can see that in our previous arrangement, it was more difficult to rotate than it is in this one. Okay, so that is a moment of inertia.